this mini course. Yeah, so there's a few questions I want to pose and answer in this mini course. This is a kind of, I would say it's this paper certainly that I am referencing here is the start of like a research theme to have kind of a purely geometric, differential geometric and algebra geometric point of view on resurgence. And I don't know how far I'll get today. Maybe I will get to an upshot today or certainly next week. One of the upshots that I want to kind of state is, so in order to prove that something is resurgent, some kind of quantity is resurgent, I want to explain that what that really means is to describe the geometry of some space that encodes the properties what we know by as resurgence of that quantity. So it's really a question in geometry rather than analysis, as it may appear at first. Okay, so the first kind of point of contact for me was through exact WKB analysis, and in particular Schrödinger equations. So okay, so let me start with a marked curve. So that's just a smooth, compact, complex curve, compact Riemann surface, and a divisor, an effective divisor. So a bunch of points with multiplicity. This divisor could be empty, or it could be interesting. So the first question is, what is a Schrödinger equation on such a global object? Well, okay, so locally we know the answer to that. Locally, if I'm working in a local coordinate, I'm looking at a second order ODE that looks like this, has this very famous Schrödinger form, second derivative, potential times a wave function. It's a singularly perturbed second order ODE, and this is key. So the fact that there is this parameter h bar appearing in the formula, you should think of it as a small perturbation parameter. So we're always interested in taking some kind of limits as h bar goes to 0, and this is kind of key. This is what makes this problem especially interesting, because this is now, it's not just a single ODE, it's an entire family of ODEs, one for each value of h bar. And there's a specific member in this family of ODEs, which is very special and very different from all the others. And that's the one at h bar equal to 0. So if I set h bar to equal to 0, at least if I do it in a clever way, then I get a problem which is completely different in its nature. It's not a differential equation anymore. And so the usual philosophy behind perturbation theory is that you find that special problem in your family of problems, which is presumably simpler. You solve that, and then you add corrections. So these would be h bar dependent corrections. And what makes this perturbation problem singularly perturbed equation is that these corrections, as I add them, they give me power series in h bar, but these power series do not converge. So if I just kind of apply perturbation theory naively on the nose, I will get some formal quantities that have a priori no analytic meaning. And the point of resurgence is to kind of negate that point of view and actually extract useful information out of these formal quantities. So this is a kind of an excellent example of a kind of resurgence problem that you might consider. Okay, so right, so so I'm looking at this ODE, second order ODE, and I'll assume that this Q, the potential, so I'll assume that it's like a polynomial in h bar, and the coefficients are some meromorphic functions of x.
With poles somehow bounded by D. Where is D?
Yeah, exactly. This is all coming, but that's exactly what you should think. Yeah, poles bounded by D, precisely. And also, actually, I want to say that the fact that I'm assuming that it's a polynomial in H bar is not so important, can generalize relatively easily. But anyway, let me stick with the polynomial case. So what about globally? So how do you think of this globally? So the guiding principle is that I want to retain this Schrödinger form of like having a second derivative time plus the potential, and I want to retain that form in every coordinate chart. And if you just look at this equation and you change a coordinate to a new coordinate x tilde, you will see immediately that there's like a first order derivative term popping out, and that breaks the Schrödinger form. And so you want the quantities in your formula, q and psi, you want them to transform in a specific way that eliminates that first order derivative term, so that you retain the Schrödinger form.
Yeah,
and so
but
that
I'm a bit confused. So is it really important? Because, you know, there is this notion of H-bar connection, lambda connection due to delink. So the limit, so what is written is just this H-bar connection. Is it really important that it's a Schrödinger or some other form? Why not to work in a bigger generality?
No, absolutely. I could. So in this paper, I just focused on this. It has its own interesting consequences of focusing on this particular case of a Schrödinger equation. Basically, in terms of H-bar connections, you're looking at an SL2 jet bundle of a line bundle. So that would be what a Schrödinger operator is. So if you want, in terms of
you take a spin bundle in this particular. Okay.
Yeah, absolutely. Yeah. So it's the whole thing can be generalized indeed, but anyway, this is the playground that I wanted to focus on. Right. Okay. And so the right. So this preference of wanting to retain the Schrödinger form imposes some very special transformation laws on the potential Q and on the wave function psi. And in particular, you see that this wave function psi needs to transform in this funny way, where the transition function is this square root or minus square root of the Jacobian of the coordinate transformation. So what this implies is that when you're talking about a Schrödinger operator on a Riemann surface, you're talking about a differential operator on a very special bundle. That's exactly the bundle that Jan just mentioned. So it's a spin bundle. By definition, it's the square root of the canonical bundle. Square root is just a line bundle on X, which I'm denoting with this funny notation, omega, a very suggestive notation. So a square root of a line bundle is another line bundle, together with an isomorphism, where if you square it, you get the line bundle whose square root you're taking. In general, square roots of line bundles may not exist. For example, a necessary condition that you can immediately deduce is that because the degrees of line bundles in the tensor product add up, if I'm squaring a line bundle, its degree will get multiplied by 2. So that means the line bundle whose square root I'm trying to take must have even degree. And one thing that we do know about the canonical bundle is that it does have even degree. It's 2 minus 2g. So these square roots exist. They're not unique, but there's always like a finite number of them. So okay, so another cool thing about this line bundle, and this is why we always get away when we're talking about Schrödinger equations, that's why we always get away with just writing down a local expression, is that once you pick a local coordinate, you get like a canonical trivialization of all these bundles. They get kind of completely canonically presented to you as soon as you choose a local coordinate. So of course, the canonical bundle has the famous coordinate dx, and then the spin bundle, because of this isomorphism is part of the data of a spin bundle, you get a local generator, which I'm denoting by dx square root. that thing is determined up to sign, so almost unique, but unique for all intents and purposes. And then, so then using this, you can define Schrödinger operator on this marked curve. So, okay, I'll give one definition. It's an H-bar family of maps, C-linear maps of sheaves. So you take a section of this spin bundle, and you output a section of the spin bundle valued in quadratic differentials. So that's what makes this map a second order differential operator. So I'm using here slightly non-standard notation where I'm putting kind of I'm thinking of this as the canonical bundle of the marked curve x comma d, but it's just the usual canonical bundle twisted by d. And so when I square it, I'm squaring the entire bundle, so the divisor gets doubled. Okay, and so kind of at this point, this is just a definition of a second order differential operator. What I want is for it to retain this Schrödinger form, and that I'm requiring that in every coordinate x, with respect to this canonical generator square root dx, that it has this Schrödinger form. Does this make sense? So then a Schrödinger equation on a marked curve is an equation where I'm searching for H-bar families of local sections of this spin bundle. And so these these local sections of the spin bundle which satisfy a Schrödinger equation are wave functions, global wave functions.
Yeah, it's sort of a pedantic question, but your family of connection, whatever, differential operators depends, of course, holomorphically on H-bar, that's fine. So when you speak about family, I understand. Now, when you speak about solutions, this psi capital, so what do you mean?
Yeah,
family. Yeah, but,
right. Yeah. Right. I'm not being clear about this here, but essentially, you could say a local wave function is something that is defined on an open subset of the H-bar plane, and satisfies this equation. And in particular, I want to look at sections which are defined in sectorial neighborhoods in the H-bar plane, sectorial neighborhoods of the origin, and with asymptotic properties as H-bar goes to 0 in those sectorial neighborhoods. So
inside the holomorphic in H-bar.
Yeah, inside that they're holomorphic in H-bar. Mm-hmm.
Okay. Mm-hmm.
Yeah. Right. So there's a small remark already been pointed out. There's a better way to define all this. You can use jet bundles. Well, in this case, you would need to use relative connections because you want to have a family over the H-bar plane, and then this object that I defined is really an SL2. It is a connection on an SL2. Sorry, it's an SL2 connection on a jet bundle of a line bundle of this spin bundle. That's one way to define it, and that's probably a better definition because it certainly generalizes much better than anything that's written in this box. Right. Okay. So suppose I have a Schrödinger operator on such a marked curve. So what do I get out of it? Well, okay. So first thing to observe is if I look at the potential, and if I look in particular at the leading order part of the potential, so Q0, the leading order coefficient, and I look at how that thing transforms under the coordinate change, then I find a formula that looks like this, and in particular, what I'm seeing is that the quadratic Jacobian of the coordinate change is popping out, and so what that means is that the leading order part of the potential is transforming like a quadratic differential. So by definition, a quadratic differential. So these are just local expressions for a global holomorphic section of this line bundle. So second tensor power of this canonical bundle of the marked curve. And I'm saying that it's a global holomorphic section of this line bundle, but it's a meromorphic quadratic differential. I'm just thinking interchangeably where I'm thinking of phi as a meromorphic section of the standard line bundle of quadratic differential, or a holomorphic section of the logarithmic quadratic differentials. And okay, so here let me kind of state all the assumptions that I'll actually need for my main result in a few slides. So okay, so the first assumption is some very typical assumption on the size of the divisor, basically just to ensure that a Schrödinger operator actually exists, and that's just computing just computing the size or the dimension of this vector space of meromorphic quadratic differentials. So if I'm on P1, then if my divisor is empty, then I have no Schrödinger equations. So assuming something like this is very standard. Then there's the second assumption. That one is important. I'm going to assume that this quadratic differential phi has only simple zeros. This can be generalized, but anyway, it's best to assume that you have simple zeros. And I'll mention why this is important on the next slide. Then there's a third assumption, which is really kind of a bookkeeping assumption. So I'm just saying that whenever I talk about a Schrödinger operator on a marked curve x comma d, I want d to be minimal. What I call minimal with respect to phi just means that I cannot make the multiplicities of points in d any smaller whilst retaining my meromorphic quadratic differential with poles along d. So in other words, kind of very concretely, what this says is that if I have a point p in my divisor with some multiplicity k, then I'm going to assume that the quadratic differential that I've picked is such that it has a pole at p, and the pole order is either 2k or 2k minus 1. No less, no more.
Is this the last assumption essential for Resurgence result?
No, this one, it's just this, as I said, this is just bookkeeping. So when I say a Schrödinger operator on x comma d, I want this. Otherwise you basically, you can think of it this way. If I have a point p in d of multiplicity k, but phi has a pole of order like 0 or 1 or something, then the way I would interpret that is that phi as a holomorphic section of this canonical bundle of the marked curve has a higher order 0 at that point, and that is again, it's not essential. You can do Resurgence with that, but it's just you need to do a few more operations to make it work, but it's not essential. Does that make sense?
Well, yeah, it makes some sense. Yeah, I understand that the quadratic differentials, it's very helpful, but okay, so but I mean, if I imagine this framework of Gayota-Murinetsky, so of course SL2 connections, it's great, but it just, I mean, everybody believes that there is a bigger generality which produces not only quadratic differential, but actually some more general object, and the Resurgence should hold.
I agree, and I'll say a few words about that. But basically, actually, this project grew out of trying to
make sense. Yeah,
trying to make sense of the higher order. Yeah, I just realized that.
Yeah, and also Mark remarked that this assumption, he means this minimality. Marco, do you mean this minimality assumption that D is determined by the quadratic differential?
Mm-hmm.
Yeah, okay.
Yeah, exactly. Yeah, that's right.
Okay. Mm-hmm.
Yeah. Okay, and then there's the last assumption, number 4, and that one actually is important. Without that assumption, kind of the tools would be quite different. But the assumption is that basically the higher order coefficients of Q are no more singular than the leading order part in Q. So kind of the quadratic differential really controls the singular behavior of the equation. So that one genuinely is important, and dropping that would need, well, for people who kind of have heard these words, it would propel you from the world of summation to the world of multi-summation, which is a step up. Right. Okay. Does that make sense? Okay.
Yeah,
so
it does.
yep.
Yeah, go ahead.
Okay. Okay. So next thing, what else do you get out of a Schrödinger equation? Well, okay, we got a quadratic differential. We can use the quadratic differential to draw an interesting algebraic curve. So for that, I need to explain that. So when you have a marked curve, there's a slight generalization of the usual cotangent bundle, which is you could call it the wild cotangent bundle or logarithmic cotangent bundle. And what it is, well, kind of the way I'm defining it here is very simple. You just take this line bundle of the canonical bundle associated with the marked curve, and you just take its total space. This turns out to be a surface. It's a holomorphic two-dimensional manifold sitting over X. Well, it's essentially just like the cotangent bundle. In fact, if I try to kind of trivialize it locally away from the points in D, then it's literally just the cotangent bundle. There's a canonical isomorphism between them. But if I'm trivializing it in a neighborhood of a point in D, then they're quite different. So probably the best way to explain it is by looking at the canonical form on this surface, also known as the Liouville one form. So just like in the usual cotangent bundle case, the total space of the cotangent bundle has a one form. So in this case, so that one form is like y dx. Dx is x is a local coordinate on X. Y is the linear fiber coordinate in the cotangent bundle. And so if I'm doing this trivialization away from a point in D, then this is just the usual, very familiar formula for the canonical one form. But if I'm trivializing it around a point P in D, and let's say the multiplicity of that point is K, then my the generator of the vector space above P of covectors, my generating covector is no longer dx. It's this meromorphic covector, x to the minus k dx. I'm just treating it as my generator. So y now, the linear fiber coordinate, is the fiber coordinate in terms of that generator. So it is in this space, inside this logarithmic cotangent bundle, that you find. Yeah, sorry.
In what sense you call that cotangent bundle is logarithmic?
Well, so there's a few things to say about this. So first of all, that's kind of a standard terminology in algebraic geometry that you have kind of omega.
You have a device called the logarithmic.
Yeah, exactly. But maybe another thing to say is that there's something cool about the cotangent bundle, which is that it's a symplectic surface. The most famous symplectic surface, and this logarithmic cotangent bundle is also almost symplectic. It's log symplectic. So it also has a two form, a non-degenerate two form on it, but that two form has logarithmic singularities along the fibers which I've modified, so that these are exactly the fibers above D.
I see. Okay, thank you.
Right. Okay, so inside this two-dimensional surface, I have a divisor. So it's the way you should think of it is it's the Riemann surface of square roots of my quadratic differential. My quadratic differential is quadratic, so it begs to be taken a square root of, and this Riemann surface is exactly what is trying to achieve that. So it's defined literally by this algebraic equation where on the left-hand side, this is my canonical one form, which is testing all the possible values inside the fibers. In this case, it's a fiber above P. And the points in which my spectral curve, this divisor, is intersecting that fiber are the ones that are given by this equation. So there's two of them. There's always two of them, unless phi has a zero, right? That's when I would get ramification. So a few kind of immediate, interesting, good common facts about this spectral curve is, so first of all, it's a smooth, compact curve. You can compute its genus. Very simple. It's a double cover. It's a double cover of X, branched. So just like any Riemann surface of the square root, it's a 2-to-1 cover, and this one is branched exactly at the zeros of the quadratic differential, and also at the odd order poles. So okay, so as a double cover, it has another piece of structure, which is this global involution iota, which just sends the fiber coordinates to its negative. And then last but not least, really important, is that this Liouville form, the canonical one form on the logarithmic cotangent bundle, that thing restricts to the spectral curve and gives me a global differential on sigma. This canonical differential is singular. It has poles, and it has poles precisely at the points where the spectral curve intersects the fibers above the divisor. So, okay, so there's a bunch of notation that I'm introducing here. So there's this delta, which is a divisor on the spectral curve. And the way it's built is that I'm taking the divisor from downstairs, D, and I'm pulling it up to the spectral curve, pulling it up as a divisor, so keeping track of all the multiplicities. And then I need to remove some copies of the ramification locus. Ramification locus is sitting above where the quadratic differential has zeros or odd order poles. And so it's this is a difference not as divisors, but I have to remove two copies of the ramification locus only where it intersects the pullback of D. Yeah, so in particular, if I assume, for instance, that I'm in a very vanilla situation where I don't have any odd order poles, very typical situation to assume, then this difference between these two divisors is equal to pi pullback D. So the ramification locus and the singularity divisor, they are completely disjoint. Right, and so this canonical differential is a global one form with poles precisely along this divisor delta. Okay, does it make sense? Any questions so far? Okay. Okay, so I want to now talk about the WKB method, which is a very powerful technique, and I want to kind of understand it a little bit more geometrically. Okay, so suppose I have this Schrödinger equation on this spin bundle, and okay, let me choose a local coordinate x so that I'm looking at an actual Schrödinger equation in a coordinate x. Okay, so here is it's a kind of a fact from basically 100 years ago, almost 100 years ago, and further than that, really. And that is, it turns out that this equation is pretty simple to solve in what could be called exponential power series. So an exponential power series is just like a power series in h bar, but it has an exponential prefactor. Or said differently, the way I wrote it here is that it's an exponential of a Laurent series. Laurent series where the negative power coefficients, there's only finitely many of them. So in this case, it's the simplest Laurent type series. It just has one negative power of h bar, and the rest is all positive. So, right. Okay. So let me kind of. I think I will emphasize it again, but I just wanted to say that this is. It's kind of remarkable that this is possible to do. These coefficients yk are pretty easy to compute. And it's remarkable that this is possible to do because kind of it's well known that these type of differential equations, second order differential equations, are basically impossible to solve in closed form. There's no way. Even for the simplest for the simplest choices of potential, there are no closed form solutions. They just don't exist. So being able to plug this kind of expression in and actually compute and have basically as good as a closed form expression for a solution is truly remarkable. So it was actually kind of why this method gained so much popularity 100 years ago in quantum mechanics. Okay, well, anyway, so you plug this in, you compute, you get all your formulas for yk, and so then you inspect what you got. And the first thing you notice is that if you look at the leading order part, why not? Then this coefficient actually satisfies precisely the same algebraic equation as the linear fiber coordinate in the cotangent bundle, y, which I called little y. So in other words, if I look at this differential y0 of x dx, that is nothing but a local expression for the canonical differential on my spectral curve. That's all it is. So the leading order part of the formal WKB solution is really just integration of the canonical one form on the spectral curve, along paths on the spectral curve. So I'm going to write it that way. That kind of immediately that suggests to me that whatever this object is, formal WKB solution, it really properly lives on the spectral curve, not on X. Another way, a more pedestrian way of saying it is that when you write this expression down and compute it, you see that there is kind of an overall square root ambiguity, which can only be resolved by passing to the double cover, which is the spectral curve. So I'm writing it here this way. So you pick any 2 points, P naught, your base point, and some P, where you're evaluating your formal WKB solution. These are 2 points on the spectral curve. And what I'm going to do is I'm going to integrate my canonical one form from P naught to P. Of course, this quantity basically, as written, only makes sense for P very close to P naught. Otherwise, I need to replace this with a path, or a homotopy class of a path on the spectral curve, starting at this base point P naught. And actually, it's such a simple observation, but it's actually kind of absolutely crucial to Resurgence, which hopefully I'll make clearer, maybe not today, but next week. Well, in any case, so you get, I'm rewriting slightly this form for the formal WKB solution. So I have this exponential prefactor, which I'm now understanding very, very well geometrically. It's just basically just a period type integral. I'm just integrating the canonical one form on the spectral curve along paths, times some as of yet not well understood a priori formal power series in h bar, which I'm calling A. Okay, so this leading order part, y naught dx, that was immediately, we recognized it to be a differential form on the spectral curve. Great. So you could suspect that maybe, okay, this whole thing that I'm integrating, in the exponential, is some interesting differential form on the spectral curve, and I'm just integrating it over paths on the spectral curve. But that is not the case, because if you look at this one form, y hat of x h bar dx, irrespective of what's going on with H bar, formal, convergent, we'll come to that. So irrespective of that, the point is that this quantity is not a well-defined differential form on the spectral curve. What I mean by that is that, I mean, of course, what I wrote here is a differential form. So what the hell am I saying? What I mean by that is, you see, I got this differential form y hat dx from choosing a local coordinate x and writing my Schrödinger operator in that local coordinate as this Schrödinger equation in a coordinate. Now, imagine I picked a different coordinate, x tilde, and repeated the analysis. So I wrote down a different coordinate representation of the same Schrödinger operator. I plugged in a similar looking WKB ansatz, but with respect to the x tilde coordinate. I would get like a y tilde hat integrand, and I would compare it with y hat integrand, and I would find that that this y hat dx does not transform like a differential form. Because, you know, if it were a differential form, I would just have this part of the transformation law. But there is a discrepancy, which depends on Q naught, or the logarithmic derivative of Q naught. So y hat dx is not a differential form because it does not transform like one. But okay, next very simple observation. Again, if you just stare at this formula, you see that well, I mean, you've already kind of even extracted this for us, which is that this discrepancy in transforming like a differential form is really occurring only at the h bar to the order 1 part. So it's just y1 which is screwing things up for us. So then there is a kind of a very simple lemma that if you look at this thing that is screwing up the transformation law for us, that actually can be interpreted as giving us a preferred local generator for the anti-spin bundle. So there's kind of a small, simple lemma that if I look at the anti-spin bundle, okay, pull it up to the spectral curve, everything is now on the spectral curve, so everything has been pulled up. Then if I look near this base point P naught that I have picked, then there is a canonical, again, up to sign, pretty much everything is up to sign. There's a canonical generator of this anti-spin bundle near P naught, and it's literally just given by this equation. And so, you know, to prove this lemma is very simple. You just see how this quantity transforms under the change of coordinate, and you will see that it's invariant.
Can you go back to the previous page on the Q0 you mentioned?
Q0.
Yes, you have
quite a while ago. This you mean?
Well, actually, the next page you have.
Next page.
Oh, the Q0 is that the coefficients.
Oh, this, yeah. Yeah, that's right. Q0 is the leading order part coefficient.
Okay.
Was that the question? Okay.
Yes, so that depends on x. Yeah, thank you.
Yeah. Mm-hmm. Right. Okay, where was I? Right. Okay. So actually, people who are familiar with WKB and have seen WKB in like a quantum mechanics course, we will remember that the standard prefactor when you kind of write down the WKB ansatz, there is of course e to the integral square root q. So that's just this part. Lambda was the square root of the potential of the quadratic differential. So now we're integrating it. It's in the exponent. But then there's another famous prefactor which is like q to the -1/4. And that's this generator that I wrote down here is precisely that q to the -1/4 that appears in the standard WKB ansatz formula. It turns out to be this local canonical generator screaming at us.
I have a sort of, I don't know, it's either a question or comment, but let me formulate it as a question. So you consider this expansion in integer powers of h bar. So,
Right.
but in principle, you can allow some fractional powers as well.
Yeah, yeah.
Yeah.
Yeah, yeah. You could try and plug in a Puiseux series of some form, but I actually don't really know what happens. At least if you plug in kind of a simple Puiseux series with like a square root h bar or something, then I think that's the only one I've ever tried actually. If you plug in a square root h bar, then what you get is a power series which are quadratic in your Puiseux variable expansion, which means that puts you back into the usual power series expansion. But of course, you could try something more bizarre, but I don't know what happens.
Okay.
Right. Okay. So yeah. So the kind of the upshot of that little lemma is that now you have this small proposition, which is you can kind of give a much more invariant formulation of what the WKB ansatz or formal WKB solution actually is. So now I'm writing this down as a section of the anti-spin bundle, and I'm saying that if you have a Schrödinger operator on this marked curve, then that has a formal WKB solution defined on the spectral curve, or alternatively, you could phrase it differently and say that you have a basis of two solutions, two formal WKB solutions, which are enumerated globally, enumerated by the sheets of the spectral curve. And the expression for this formal WKB solution is like this. It's written in terms, so I've already fixed a base point, P naught. That's part of my assumption. I have a base point P naught. That base point P naught gives me a canonical local generator of the anti-spin bundle, the pullback anti-spin bundle. That's what I'm calling E naught. And then the rest is now just a function. The rest is just a function, and that function looks like this. It has the kind of period-like integral of the canonical one form, and it has the other factor, which is also an exponential integral of a power series valued in differential forms. And so this lambda hat is now a global, or I should say it's a power series in h bar whose coefficients are global differential forms on the spectral curve with poles. So first of all, along along delta in the prescribed way, just like you had. But in addition to that, they have this funny behavior that at the ramification locus, they also have poles, and these poles grow in order as the order of h bar is increased. So in other words, it's a global section. Each coefficient is a global section of this omega sub sigma delta of star r. Okay. So this object seems important. So I give it a name. It's called the formal WKB differential. It's associated not just with the spectral curve. The same spectral curve could have many different formal WKB differentials. It really includes the information of the Schrödinger operator itself as well. So it really needs to know about your full potential Q. Okay, but then the next thing is I'm having a global differential form on the spectral curve. There's another global differential form on the spectral curve that I'm aware of, which is the canonical one form. So what I can do is just write this formal WKB differential in terms of that global one form lambda. And what I get as the ratio of the two is a function little f of h bar. Sorry, it's a function in two variables now. It's a function of the local variable on sigma and also of h bar. Well, it's actually a power series in h bar. So here I'm expanding it as a power series in h bar. It's an infinite series in h bar with coefficients which are now global functions on the spectral curve with poles only along the ramification. So this is kind of an important point. It's because this formal WKB differential. So I said it has got poles along, kind of unbounded order poles along the ramification, but also poles along the along this divisor delta. But so does lambda. Lambda has the same polar behavior, like little lambda has the same polar behavior as the coefficients of capital lambda hat along delta. And so when I'm expressing capital lambda hat in terms of little lambda hat, I'm actually removing all that principal part that's happening along delta. All I'm left with is what's happening along ramification. So I get this global holomorphic function, coefficients, each of which is a global holomorphic function, save for poles along ramification. Does this make sense?
For me, yes, but I'm not sure. People can unmute themselves if they have questions. Yeah.
I'll wait 2 seconds. Okay. Okay, so now let me speak about this function or this power series f hat. That's kind of the star player now. Everything has been boiled down to understanding this f hat. So first thing, I've already kind of mentioned it, but let me now talk about it from the point of view of f hat, and that is that the coefficients of this power series are kind of incredibly computable. And I emphasize the fact that to compute this, what seems to be essentially a closed form solution to a Schrödinger equation, you do not, at no point do you actually have to solve a differential equation. That is remarkable. That is a remarkable property. But that comes at a price. Always it does, which is that although you can compute it very explicitly by hand, this power series f hat is divergent. Pretty much always. I mean, the only exceptions when it's not divergent is when the potential is like constant or at least non-vanishing. So as soon as the potential Q has a zero, that's it. The thing is necessarily going to be divergent. So okay, so then the goal of kind of the improved WKB method, we're heading towards the exact WKB method. The goal is to lift this formal power series in h bar to an analytic function, f. Analytic both in the local variable on the spectral curve and in h bar, in some, hopefully some sectorial neighborhood of the origin in the h bar plane. So holomorphic function into variables. And so that way you would get a true solution. And well, okay, so first fact is that this can actually always be done. The fact that such a lift exists is a relatively simple, very classical fact from asymptotic analysis. It's called the asymptotic existence theorem. You can always lift. Basically, the way that works is that you know that you can always lift a formal power series, an asymptotic series, to a true holomorphic function. So you start with f hat, you lift it to some f tilde, which is an arbitrary lift that is not necessarily going to be a solution to your differential equation. And then what you need to do is you just need to write down a new equation for the correction between f hat, between f tilde and what should be the lift solution to your equation. You write down that equation and you can solve it for a correction, and so you can always lift it. The problem with that approach is that these lifts are they're non-canonical. There's no way to make them canonical. They're highly non-unique. Even kind of describing the space of all possible lifts, it becomes some kind of huge, impossible, large space. So this approach, you're typically never going to get any kind of uniqueness statements, and even constructability is very difficult. So these solutions are non-unique, non-constructible.
So I'm confused. When you say that it's always can be done, do you mean in sectors, or you mean...
In sectors. So the typical kind of asymptotic existence theorem says that if you have a power series and you have a sector of sufficiently small opening, there exists an analytic function whose asymptotic expansion is the given series, and this analytic function is highly non-unique. But you can always lift. Right. Okay. So new goal is to, instead of just lifting it in some nilly-willy way, try to lift this remarkable f hat to an analytic solution f, but in a canonical way, in a way that I can control. And the way to do that, basically, there is a definite sense in which the universal technique for achieving that is called Borel resummation. So let me give you a crash course in Borel resummation, one way to explain what that is, what that does. I'm going to present a very kind of a practical way of applying Borel resummation. So it proceeds as follows. So you start with your formal power series in H bar, f hat, and the first step is to apply what is called the Borel transform, or formal Borel transform. That's what I'm calling fractor B. That is a very simple, very simple operation on power series. What you do is so here's the formula for the Borel transform. You literally just take the formal power series f hat, and you essentially, every coefficient you divide by a factorial, k factorial. And there's some shift happening. So it's an incredibly simple operation. Right. So now I have a different power series. I had a power series in H bar. I've converted it into a power series in T, some auxiliary variable T, sometimes called the Borel variable. So the next step is to take this power series, think of it as a holomorphic germ at the origin in the T plane, and construct analytic evaluation of this power series in some direction. So let's say I picked some angle alpha, a ray that gives me an infinite ray in the T plane, and my goal is going to be to take this phi hat, this holomorphic germ, and apply the Laplace transform to it in the direction alpha. So that means I will be integrating phi hat along a straight ray in the T plane in the direction alpha. So I will be able to, if I'm able to analytically continue it, and on top of that, I apply the Laplace transform, which is some kind of improper integral. If that thing converges, then I get an analytic function of H bar defined in some sector of the H bar plane. The analytic function depends on alpha. If I change alpha, basically all bets are off. So here I'm kind of summarizing essentially what I just said, which is the output, if all goes well, the output is a holomorphic function of two variables. So U is some open subset of the spectral curve. V, so here I'm explaining precisely, V is a sector at the origin, or a sectorial neighborhood of the origin in the H-bar plane, with an opening of a specific kind. It's basically kind of a half plane sector bisected by the direction alpha. And this function f alpha has a strong asymptotic property, which is that it does admit an asymptotic expansion as h bar goes to 0 in this sector. And that asymptotic expansion is f hat, the thing that you began your journey with. And here in brackets, I'm kind of specifying a bit more, maybe for experts, which is that it's what I call asymptotic expansion of factorial type, or Gevrey 1. Not so important. Okay, and then the fact, this is where kind of all these adjectives, factorial type, etc., come in important to play an important role. But the fact is that if this procedure succeeds, if you succeed in doing this procedure going from f hat to f alpha, the function that you get is actually the unique holomorphic function on such a domain, open set cross sectorial domain, such that this asymptotic expansion holds uniformly with respect to the angle of approach, and also uniformly in the x variable, or whatever variable on the spectral curve. So this so I'm calling this unique function, it's called the Borel resummation of f hat in the direction alpha. So it has this kind of completely canonical feel to it. There's some condition that this function satisfies, and it's the unique one that satisfies it. And this condition also is kind of can be made completely geometric. It has really nothing to do with the variable t, etc. All of these are totally invariant properties. So okay, so right, but there was kind of a lot of ifs in this procedure that I mentioned. So in order for this to work, several things need to be satisfied. So the first thing, of course, is that this phi hat germ, that needs to be a convergent power series in T. Otherwise, analytically continuing it makes no sense. So that's the first thing. Okay, for Schrödinger equations, that's true, and it's kind of at least in the grand scheme of things, that's an easy fact. But then the second thing that I needed before I took the Laplace transform was I needed to be able to take this holomorphic germ phi hat, and analytically continue it along that ray in the alpha direction. And that, like any analytic continuation, that is not easy. That is the most difficult part of the procedure, to be able to construct that analytic continuation. And then not only that, not only do you need to be able to construct that analytic continuation, you also need to ensure that once I've done that, and then I apply the Laplace transform, so I'm integrating it against this Laplace kernel, that this integral actually converges. That is a non-trivial requirement. But somehow, at least in all the problems that I've encountered, once you've constructed the analytic continuation, this what I'm calling exponential boundedness almost kind of comes not so much for free, but kind of as part of the construction. So I'm just calling it difficult, not very difficult. Okay, so let me just see, what else do I wanted to say? Yeah. Okay, let me try to blast through this slide, because I want to end with the statement of the theorem, and then next time I'll kind of pick up from here. But basically, so to summarize this slide, is that what our goal now is to study the analytic continuation of this Borel transform phi hat, and what I want to do is analytically continue it in various directions in the t-plane. And if as I start changing the angle alpha slightly, and if I'm lucky enough that I'm not encountering any singularities of phi, so I give kind of the sector where phi hat extends to an analytic function, everything is good, exponential bounds, then all these Borel resummations for all these nearby alphas, they kind of glue together into the same analytic function. So in other words, the result of Borel resummation is kind of constant in some sense for nearby alpha. But then, if as I continue sweeping the angle alpha, and my ray runs into a singularity, then basically in that particular direction, alpha star is what I'm calling it. In that particular direction, Borel resummation technique no longer works, or is ambiguous, or there's some kind of problem. But if I, typically, if I continue varying alpha, then maybe I'll come off that bad ray where I'm seeing a singularity, and I'll again be in one of those kind of green regions where the Borel resummation works. And the fact of the matter is that the results of the Borel resummation that I'm obtaining before I hit that Stokes ray and after I hit that Stokes ray, they are not the same. Typically, they are not the same. And so this is the manifestation of the Stokes phenomenon in exact WKB, that I have this discontinuous jump in an operation that produces, that lifts a formal power series to an analytic solution. This is a typical kind of Stokes phenomenon setup, but in this scenario. Okay, so right, so I just want to end with this slide. I'll take maybe 2 more minutes if that's okay. So the goal is to analyze the analytic continuation of the Borel transform of WKB solutions and see where that operation makes sense, where it fails, how it fails. And so this is precisely the kind of the realm of resurgence. And so here's a kind of a quasi definition, which reads as follows. So if you have a formal power series, then it's resurgent, or resurgent in a specified number of directions, if several things are true. So your Borel transform is convergent, and you have analytic continuation in that direction, and the Laplace transform is well defined. So in other words, you have Borel summability in every direction alpha, or almost every direction alpha. And for those directions alpha where Borel resummation fails, you should be able to describe the Stokes phenomenon across those singular Stokes rays. And the requirement is that this kind of discontinuous jump should be describable in terms of other Borel summable quantities. So if all of this kind of very, very strong setup is satisfied, then the thing that you're studying is resurgent. Okay, and so there's kind of an old conjecture, basically from the start of the whole exact WKB endeavor, and it's I'm attributing it to Voros and to Ekal, and so this conjecture, which I'm calling quantum resurgence conjecture. So it can be formulated like this. So we're studying Schrödinger equations and formal WKB solutions of Schrödinger equations. So in particular here, suppose I'm on P1 and my potential does not depend on H bar. And so just got this leading order term Q0, and this Q0 is a polynomial in X. So there are no poles in the complex plane, they're just poles at infinity. Then the conjecture says that if you write down the formal WKB solutions, they are resurgent in all directions. So that's the conjecture. So let me state the theorem now. So now suppose I have any marked curve, P1 or something much more interesting, and you have a Schrödinger operator on this marked curve, satisfying those 4 assumptions that I made much earlier. So in particular, the fact that the quadratic differential has simple zeros, and that the poles, very importantly, the kind of higher order coefficients of the potential, the poles are no worse than the leading order. So if that's satisfied, then formal WKB solutions are resurgent, and they're resurgent in all directions with just one exception. The exception is given by some foliation, natural foliation that you have on the spectral curve coming from the quadratic differential. And there's a type of trajectory that this foliation may have, which are called divergent trajectories. They're kind of particularly badly behaved leaves, critical leaves of a foliation. And so it is in those directions that resurgence fails. And actually, the thing that fails is the exponential type. That's the only thing that fails. And so, okay, as a kind of an obvious corollary now, we specialize this to P1, Q0 polynomial, etc. You get that the quantum resurgence conjecture is true. Okay, so I'll end here just to say a couple of words of what I'll do next week. So next week I kind of want to, the big goal next week would be to promote this quasi definition to an actual definition, to be able to tell exactly what it is that I'm supposed to prove, and I'm going to interpret it in very geometric terms, because that's the setting in which this theorem is most naturally proved. So I'll try to explain all that and kind of my point of view, my geometric point of view on resurgence. So okay, I'll stop here.
Yeah, thank you very much. So these singularities which you mentioned in the Borel plane will be all periods of the Liouville form, or it will be a subset? It
will be all periods. So it's kind of interesting. So as I'll explain next week, one needs to kind of compartmentalize the meaning of singularity. So there's a notion of singularity which I call visible, and a notion of singularity which is called observable, and others. So visible singularities are those which you can kind of reach in the most direct way by geodesics, in a strong sense of the word geodesic. And so those are kind of, in terms of like spectral networks and Stokes graph, and so those are literally given by real or trajectories for a fixed phase. So if you're sitting at a point on the spectral curve and you shoot out a trajectory of the quadratic differential for a specific phase, and that trajectory runs into a ramification point, then that is what I call a critical path. And that is a visible, that's going to manifest itself as a visible singularity in the Borel plane. Mm-hmm. But then there are other singularities which you may reach without having to follow a geodesic. So all of those singularities, they're all appearing on the Borel plane.
Yeah, this what you call visible. Maybe it's better to discuss next time. Yeah.
Right.
And I forgot there was this famous paper by Delabert, Dillinger, and Pham about this Varro's resurgence, something at the beginning of 90s. What did they prove?
Right. So I spent a long time trying to understand what was actually proved in that paper, and I've come to the conclusion that basically, so I mean, they derived this amazing formula, which we call GTP formula, which kind of like a wall crossing type formula for the Stokes automorphisms in WKB.
Yeah, it's five term. Yeah,
right.
Term relation for
right.
Yeah.
Right. So, but there is they use the fact that WKB solutions, normalized WKB solutions, etc., are resurgent, but they refer to Ekal, okay. And then so Ekal's proof is not clear, to say the least. And then in the follow-up paper, Delabert, Pham, and I forget the third author, they do comment on their use of Ekal's resurgence result, which is that it's, they kind of clearly say that there is a claim in Ekal, which actually I haven't really been able to find, but that's probably my problem. But they said that there's a claim, but not all details are clear, is I think the direct quote.
So then the problem was open. Okay. Okay, good. Now, more questions to Nikita.
Just a quick, you're going to talk next time on the corollary. And the original conjecture one is the when X is the P1. But mm-hmm. Your theorem is much more general than P1. So
that's right.
Does the corollary also say much more general as it says in the theorem? So you have a curve with a marked curve.
What? Sorry, I don't think I understood the question.
The corollary, the quantum resurgence conjecture.
Yeah.
So can you formulate that for more general, so you have marked curve?
But that's, I mean, that's the content of the theorem.
That's the theorem. So does that also? Oh, I see. So that's already said that you already have a resurgence. Yeah, that's what I was.
Yeah. I guess one thing to say is, for instance, here in the theorem, there's a clause, right, that it's resurgent in all directions except those which correspond to these divergent trajectories. Yeah. So part of the proof of the corollary, if you like, is the observation that if the quadratic differential is a polynomial in the x variable, so like in the quantum resurgence conjecture, then divergent trajectories.
There is no poles in all directions. Thanks. Yes.
Okay. So more questions or comments? Okay, if there are no more questions, so let's wait for the second lecture in a week from now. Okay, so, and thank you again, and so see you next week, as Marka sent the message to everyone. All right, thank you. This is it for today. Thanks, Nikita.
Thanks very much. Thank you.